Hi everyone, Quadian here. Chemistry with Quadian, it's our channel for chemistry students from all over the world. We will teach you every day about all of chemistry theory lessons. Subscribe our channel and press the bell button for daily lectures updates.
Dear students, Assalamu alaikum. Today we will talk about reactions of alkene. We will deeply discuss about Markovnikov rule and anti-Markonikov rule. So let's start the discussion. Reactions of alkene. The pi bond is electron-rich species and can act as an electron-pair donor. We know that alkene contain a pi bond, and pi bond is an electron-rich species and can act as an electron-pair donor. It means that it can donate its electron to electron deficient species. It means it can donate electron to its electrophile. When this alkene donates its pi bond to electron deficient species, which is known as here is proton, then it is acting as a base, and as a result tertiary carbocation is formed. This pi bond can also donate its electron to an electrophile, thus is acting as a nucleophile, and as a result tertiary carbocation is formed. So here it is one of the most important questions is that what is the difference between base and a nucleophile? This is one of the most important questions. Most of the time this question is asked in interview. So let's discuss this. Base, a species donates lone pair of electron to hydrogen. Base is a species which donates lone pair of electron to hydrogen only. And nucleophile is a species donates a lone pair of electron to electron deficient compound except hydrogen. So a nucleophile is that species which donates a lone pair of electron to a species which is electron deficient other than hydrogen. It means that both base and nucleophile are electron rich species. So in alkenes, addition and elimination reaction, alkene undergo both addition and elimination reaction. Addition and eliminations are equilibrating reactions. It means that both reactions go side by side. Which side is favored depend on the temperature. For example, here it is an alkene. When we put hydrogen halide in it, the addition reaction is favored at low temperature and we will get this product. But when we increase the temperature at high temperature, the elimination reaction is favored and we will get these reactant back. It means there is equilibrium between reactant and a product, and these reactant and product depend upon the temperature. So let's take an idea from Gibbs free energy. Gibbs free energy is the sum of enthalpy term and entropy term. We know that enthalpy is the total heat content of the system, while entropy is the degree of disorderness in a system. The sign of delta G will determine whether the equilibrium favor forward direction or the equilibrium favor backward directions. So we know that at low temperature, entropy term is small. When temperature is low, this factor would be small. Why small? Because two molecules of reactant are going into one molecule of product. So this factor will be small, while the enthalpy term is dominate. As a result, delta G will be negative, which means that products are formed faster as compared to reactants. So addition reactions are favored at low temperature. But when we increase the temperature, this entropy, degree of disorderness is increases. Why increases? Because one molecule of a compound is converted into two molecules. As a result, degree of randomness or disorderness is increases. As a result, the entropy of the system is increases, while the enthalpy term will decreases. As a result, delta G will be positive, which means that reactant are favored. In this way, we can conclude that at low temperature, addition reactions are favored, while at high temperature, elimination reactions are favored. Now let's discuss what is hydrohalogenations. Hydro mean hydrogen, halogenation mean halogen, addition of halogen. So addition of hydrogen and halide, addition of hydrogen halide to an alkene is known as hydrohalogenation. We can use HCl, HBr and HI for this purpose. The mechanism is a two-step process. First step is a proton transfer. As we know that alkene contain a pi bond. This pi bond is a source of electrons, so it will attack on this proton. As a result, this bond will shift here. The alkene is protonated, forming a carbocation intermediate. As a result, this carbocation intermediate is formed and a bromide ion. And here it's leave and a bromide ion will form. In the second step, which is one is a nucleophilic attack. The bromide ion which is formed will attack on this tertiary carbocation, and as a result we will get this product. The bromide ion function as a nucleophile. Why nucleophile? Because it is attacking on a electron deficient species which is other than hydrogen. Here it is a carbon. So that's why it is a nucleophilic attack, and the carbocation attacks the carbocation intermediate, and we will get this product. So hydrohalogenation is a regioselective for Markovnikov addition. In 1869, Markovnikov observed that hydrogen atom tend to add to the carbon already bearing more hydrogen atom. Hydrogen atom adds to the carbon already bearing more hydrogen atom, and halide ion add to the carbon bearing least number of hydrogen. Let's discuss. This is an alkene. This double bond contain one hydrogen. This carbon contain one hydrogen while there is no hydrogen in it. So when we add hydrogen bromide in it, the hydrogen will add to that carbon which contain greater number of hydrogen atom. So hydrogen will add here. As a result, tertiary carbocation ion will form here. In the second step, the bromide ion will attack there. As a result, we will get this product. We know that tertiary carbocation ion is stable as compared to secondary carbocation ion, and secondary carbocation ion is stable as compared to primary carbocation ion. In this way, the hydrogen is adding here and bromine is adding here. The halogen is generally installed at the more substituted carbon. So when peroxide are used with hydrogen bromide, the opposite regioselectivity is observed. For example, when here is an alkene, when we add hydrogen bromide in the presence of peroxide, then anti-Markonikov addition occurs. It means that hydrogen will add to that carbon of a double bond which contain least number of hydrogen atom. So hydrogen will add here this carbon while bromine will add to this carbon. This is an anti-Markonikov addition. It means that it is anti to the Markonikov additions. So we will get 95% yields. The reaction mechanism must be different when peroxide are present. So it means here peroxide is present. So that's why we will get this product 95% yield. So let's discuss some example. Hydrohalogenations. There is an alkene, cyclic alkene. When we put HBr, first step is a proton transfer. As a result, tertiary carbocation formed here. In the second step, bromide ion will attack here and we will get this product. While second example, 1-methyl cyclohexene. First step is same. This double bond attack on hydrogen. As a result, tertiary carbocation will formed. Because why tertiary carbocation? Both carbocation will form. Secondary carbocation can be formed and a tertiary carbocation can be formed. But we know that tertiary carbocation is more stable. So tertiary carbocation is formed faster, and bromide ion will attack on this tertiary carbocation and we will get this product. So in the end, the important conclusion here is that regioselectivity of HBr addition can be controlled by. How we can control the regioselectivity of hydrohalogenation? Simply when we add only hydrogen bromide, then we will get Markovnikov addition. We will get this type of product. But when we add peroxide in hydrogen bromide, then we will get anti-Markovnikov addition. We will get this product. This is a more substituted product, while this is a less substituted product. So in this way, so this is a complete mechanism of hydrohalogenations. Kindly like and subscribe our channel for latest videos. Wish you best of luck. Allah Hafiz.